Hi everyone, I'm here in the lab with my favorite rotating tank apparatus, which you can see here. And what I'm going to do here is a little experiment to look for evidence of Taylor columns. If you recall from lecture, we derived a result known as the Taylor-Proudmann theorem or the Taylor-Proudmann effect, which was relevant to motions that are in simultaneous hydrostatic and geostrophic balance. And the result specifically was that for a fluid in that balanced state, in the absence of density variations, what we would technically call a barotropic fluid, the result says that there is no vertical shear. So the horizontal velocities must be the same at every level. Okay, so that's a very strong constraint on what kind of motions are possible. So to test this, here's what we're going to do. I have tank spinning here, and as you can see, it's about half full of water. There's the circular insert inside of the square tank, and if I look down at the meter here, I can see that it's rotating right now. What that means is 5.2, 5.3 rotations per minute. Okay, and of course up here, as we know, we have the image from the co-rotating camera that lets us observe what's going on in the rotating frame. Now, you'll see something in the tank. Down at the bottom, if I look in cross-section without all the reflections, what you see is a hockey puck, okay? It's just sitting on the bottom of the tank, okay? If we look at it from above, of course, there's some distortions of the image because it's passing through water, but there's my hockey puck. And of course, in the rotating frame, it appears to be motionless. Okay, so the puck, I have another one right here. It just looks like this, right? It's just a regular old black hockey puck. So my experiment is actually to see if I induce a little bit, this tank has been spinning for quite a while. It's in solid body rotation. My experiment is going to see if I induce a small amount of relative velocity in the tank. I'm going to try to measure if parcels of water pass over top of the hockey puck or not. And if the Taylor-Proudmann result holds, then we should not find that parcels of water are traversing the location of the hockey puck, because at the level at which the hockey puck is sitting, no such motion is possible because there's a puck in the way. And if there's no shear in the flow, then at every level we should also find that parcels have to go around the puck rather than over the puck. Now remember that this result applies only at very small Rossby number. And so what I'm going to do is I'm going to induce a motion in the tank by reducing the motor, the speed of the motor, just a tiny bit. And that's going to cause the water in the tank to rotate slightly faster than the tank itself. So there'll be a relative velocity that's induced, but it will be small. So the Rossby number, U over F over L, will hopefully be a very small number if I keep U very small. And the way to do that, of course, is just to move the knob that controls that motor just a tiny, tiny bit. Now, to visualize what's going on, I'm going to go here and grab this very high tech here. These are just dots of paper, okay? I'm going to take some and put them in my hand while I'm holding the camera. Okay, these are just purple bits of paper, and I'm going to sprinkle them on the surface of the tank, being careful not to nudge the tank while I do it. And what I'm basically trying to do here is put dots in the location that's going to be upstream of the barrier when I induce that motion. So I'm trying to get my last couple of dots here, but they're not coming out. Okay. So if I look now in the co-rotating image, of course the dots appear stationary, just like the puck, which is good. That's evidence of something very close to solid body rotation here in the tank. So I'm ready to start the experiment. So what we're going to do is I'm going to go over down here to the control knob, which is that brass knob there, and I'm going to make a very small change. I'm going to do it carefully. going to look and see what happens. So we're going to focus on the image in the co-rotating camera here. Now you can see those dots are moving. They're moving just a little bit. U is very small, so we should be at a very low Rossby number. So what we're looking for is evidence of paper dots seeking a path that goes around rather than over the top of that hockey puck. There are a couple dots that seem to have crept over top of the puck. Do we see them now moving to one side as if they're at least approximately skirting the perimeter of the puck? Now remember, if I go over here and look at the cross section, those paper dots are all floating on the surface. Can we see that? They're floating, so they're nowhere near the puck. The puck is way down there. So if we see evidence here in this image that the paper dots are going around that hockey puck, then what that's telling us, I think, is that information about the presence of the puck is somehow known, to the flow at the very top of the tank. And I think it's pretty clear. I see it. I hope you see it. None of those dots have taken a path that go directly over top of that hockey puck. So it's kind of amazing, but it's a demonstration of this phenomenon that we call vertical rigidity at small Rossby number. In the absence of density variations, we have this very strong constraint that there can be no vertical shears in the horizontal flow. And that is our demonstration of the phenomenon known as the Taylor column. Let's wait one more minute and see what these dots do. We've just arrived at the edge of the puck. Of course, eventually, U is going to spin down due to frictional effects, and the the relative flow in the tank will go back to zero. And the longer we wait, the less likely it is we're going to see motions that are very well approximated by geostrophic balance as frictional effects come into play, but it's still worth watching. And I would argue that once again, you see those purple dots, rather than going right over the puck, seeming to be deviated to one side. There we are. There's our Taylor column.